So let's say that we have a ground that looks something like this. So up to this point, the ground is flat, but after this point, the ground becomes quadratic shaped, and we're going to say that this ground obeys the equation y equals negative kx squared, right? It's a quadratic ground. We'll call this point the origin, and suppose that we have a ball located at the origin. If we kick the ball into the air, let's say it follows some trajectory like that. And we're going to suppose that the ball intersects the ground at that location. We'll suppose that we kick the ball with some initial velocity v0 at some launch angle theta. We'll suppose that we have some acceleration due to gravity g. Here's the question we're going to answer in this video. So given k, theta, and g, find the smallest initial speed that we kick the ball at, such that the ball never even hits the ground. So a way to visualize this is that with this particular initial speed, we kick the ball and the ball hits the ground. So clearly we would need a larger initial speed in order to never hit the ground. You can imagine if we kick the ball at a larger initial speed, it might form a trajectory that looks something like that. And as you can see, the ball is clearly never going to hit the ground. But what is the smallest initial speed that makes this possible? That's the question we're going to answer in this video. And our final answer should be in terms of these three things. In other words, k is a number that determines the shape of the pathway, theta is the launch angle, g is the acceleration due to gravity. So each of these three things are constant throughout the problem. So how do we actually solve this problem? Well, it might be a little difficult to consider what happens if the ball never hits the ground, because we don't even know if that even happens, right? We haven't even proved that there exists a case where the ball never hits the ground. So let's consider the case where the ball actually does hit the ground, right? Suppose that the ball hits the ground at dx comma dy, where dx would represent the horizontal displacement of the ball from here to here, dy would represent the vertical displacement of the ball from here to here. And so really, what we're going to want to do is we're going to want to get an equation that relates all of these things together. And how in the world do we do that? Well, it's really just a projectile motion problem, right? We can analyze the horizontal and vertical motion of the ball. As for the horizontal motion, we know that when it comes to projectiles, in the horizontal direction, we get constant velocity. So really, we can use this equation, where dx is just the horizontal displacement, which we'll just say dx. Vx is the horizontal velocity. And in this case, it's just the horizontal component of the initial velocity, v0 cosine theta. T is just t, right? For the vertical motion, well, we know that when it comes to projectiles, in the vertical motion, it's constant acceleration because it's the acceleration due to gravity. Therefore, since it's constant acceleration, we can use a kinematics equation. More specifically, we'll use this one. Right? dy is just the vertical displacement. We'll keep that the same. Vy0 is the vertical component of the initial velocity. So really, the vertical component of this would be v0 sine theta. As for ay represents the vertical acceleration, or for our purposes, just the acceleration, right? The acceleration due to gravity. But you have to be careful, because since the acceleration is pointing downward, it has to be negative. Therefore, we have to put a negative sign in front of g, right? Because inherently g is a positive number, right? G is positive 9.8, so we got to put a negative sign in front of it, so that assures us that our acceleration is negative. And so this is what we have now. And I can rewrite this as like that. Now, here's what we're going to do. First thing is, it turns out that we can rewrite what dy is in terms of dx, because dx comma dy is a point on this curve, right? We can substitute dx into x and dy into y. We would get this. And so now I'm just going to replace it with negative k dx squared. So this is where we're at. And so now, notice that we have t here, right? Well, t is completely irrelevant to the problem that we're solving. So we're going to want to eliminate it. What I'm going to do is I'm going to solve for t in this equation. You would get this. And so now what I'm going to do is I'm going to substitute t in the other equation for what I have here. So if I do that, I would get so basically we've written an equation where t is completely eliminated, which is good. And notice v naught cancels out. And so what we're left with is dx, but then sine theta over cosine theta is equivalent to tangent theta. And as for what we have here, what I'm going to do is I'm actually going to combine this into one fraction. In the numerator, you would get g dx squared. In the denominator, you would get 2 v naught squared cosine squared theta. And that's basically what you get. And another thing I'm going to do is I'm actually going to rewrite cosine squared theta as secant squared theta in the numerator, just because it looks nicer for me. And right, you know that secant is just the reciprocal of cosine. That's why we can do that. And so what you need to realize here is we have an equation that relates these 5 things together, right? What I'm going to do now is I'm going to algebraically solve for v naught in this equation. So we're algebraically solving for this variable, v naught. Actually, you know what? We're going to solve for v naught squared, because we're going to have to solve for v naught squared if we want to solve for v naught, right? So solving for v naught squared, I'll first start by eliminating the fraction. Right, I'm going to multiply 2 v naught squared on both sides. If I do that, then on the left side I would get, and on the right side, if I distribute the 2 v naught squared across, well then for the first term I would get, and for the second term, the 2 v naught squareds cancel out, and I'm just left with what I have in the numerator. Just like that. Now, another thing to notice here is that every single term, all 3 terms, have a dx in it. So I can divide dx on both sides. And so notice dx would cancel out like that, dx would cancel out like that, and like that. And so what we're left with on the left side is, and on the right side we would get this. Now remember, our whole goal is to solve for v naught squared. And what we can do at this point is we can group the terms that both have v naught squared in it. To do that, I'm going to add this to the other side and add this to the other side. Doing that, I would get this. And so as you can see, the terms with v naught squared are now grouped together. So now I'm just going to rewrite this back at the top. So now what I'm going to do is I'm going to factor out v naught squared on the right side of the equation. And so that's what we get. And then now I'm going to divide this parentheses to the other side, and that would solve for v naught squared. And so now we have solved for v naught squared. Remember, this equation is still completely in terms of these 5 things, but we've solved for v naught squared. And really, this doesn't tell us anything about the value of v naught such that the ball never hits the ground, because dx can be a finite value. But in order to think about what happens if the ball never hits the ground, another way of looking at that is thinking about what happens if this point is infinitely far away from our starting point. In other words, what happens if dx approaches infinity? Right? So what we're going to do is we're just going to take this expression and think about what happens as dx approaches infinity. So now we're going to basically rewrite this as a limit to get to the v naught that we really want to solve for. And so this is the limit that we have to evaluate. And we love evaluating limits, right? Because it's calculus, right? We love doing this, right? I like that. That was good. Okay. But evaluating a limit like this is in the same form as if we were to evaluate a limit like this one. It's really in the same exact form as this limit. And to evaluate this limit, it turns out all you have to do is take the coefficients in front of the x. And the answer to this limit would be 9/4. Right? That's all you have to do to evaluate a limit like that. And the same thing goes for anything that's in that same form, right? So really, in this case, our variable is x, but in this case, our variable is dx. So we're focused on the dx's, right? As for the numerator, right? The g secant squared theta would be our coefficient, because that's what the dx is multiplied by. In the denominator, the coefficient in front of dx would be 2k. So now we know what the answer to this limit would be. In the numerator, it would just be g secant squared theta. In the denominator, it would just be 2k. And so this is the value of v0 squared such that dx is infinitely large, right? So if this point has an x value that is infinitely large, then this is what the initial speed squared would equal. It would be this, because that's what the limiting value approaches. And so now we just take the square root to get v0, and we would get square root of g/2k secant theta. And so this would be the initial speed such that the ball never hits the ground. In fact, it would also be the smallest initial speed such that the ball never hits the ground. And so this is basically how we would solve a problem like this, right? We think of this point as if it approaches infinity, right? We think of it as if dx is really, really big. Well, then it turns out this would be the v0 that causes that to be true if we let dx approach infinity. And that would suffice that the ball never hits the ground in the first place. And so this would be v0. And yes, notice it's in terms of k, theta, and g. It's exactly how we wanted it to be. And so this is basically it for this video.